Hello everyone and welcome back to our quantum key distribution series. In today's lecture, we will dive deeper into the fascinating world of quantum measurements. Measurement is a crucial aspect of quantum mechanics, especially in QKD, where it plays a central role in securing communication. We'll start by understanding how single qubits are measured in different bases such as the computational and diagonal bases. Then we will expand our discussion into multiple qubits, exploring how measurements work when dealing with entangled or composite quantum states. These concepts are crucial and essential for grasping how quantum protocols operate and how information is securely extracted and shared in QKD systems. So moving on to the concept of measuring a qubit in an arbitrary basis. So we have discussed the case of measure the qubit in computational or standard basis. So in today's lecture or in upcoming slides with the help of example, we will discuss and show that how can we measure the qubit in any arbitrary basis that could be standard basis or any kind of diagonal basis or any basis that we uh, want that of our desire. So consider we have a state in terms of computational basis that is the 0 and 1 state, and the qubit is written as the superposition state of these bases, and it is given in equation 1. So we want to calculate the given qubit in the basis V0 and V1, and these could be any basis of our desire and choice. So we will first write the basis, the given state in terms of these bases, and uh, this will obviously change the probability amplitudes associated with that outcomes, and we could get the probability of outcomes by taking the mod square of the given complex amplitude that has been modified by changing the basis of the given state. So that's how we could calculate any given state in arbitrary basis. So let's move on to the example. So we have a state in equation 4, that is the superposed state of 0 and 1, and it is written in as we could see in the standard basis. So our goal is to write first is our first goal is to write the given state in the Hadamard or diagonal basis, that is the basis plus and minus. So we could see that we could write this as in terms of the plus and minus basis in equation 5. So the probability amplitudes associated with the given state are 1 and 0. So we could see that the probability of getting plus state or plus outcome is 1, and probability of getting minus outcome is 0. So that's how we could calculate any kind of state in arbitrary basis of our device, of our desire and choice. So moving next to another example, and that is the more general case where alpha and beta are probability amplitudes and they are arbitrary amplitudes that could take any kind of value. So similarly, as discussed in previous slide, we want to calculate the probability associated with the outcomes in the measurement basis of plus and minus. So we would write the 0 state and first 1 state in terms of plus and minus, and we will plug in that values in equation 7. So after rearranging the coefficients of plus and minus, and we could see that the psi takes the form of uh, uh, plus and in terms of plus and minus in equation 9. So we could see that the probability amplitudes are modified, and they are given as alpha plus beta over square root 2 for the plus state and alpha minus beta over square root 2 for the minus state. So we could see that the probability amplitude associated with the outcomes plus is the plus alpha plus beta over square root 2 mod square, and the probability associated with the outcome minus is alpha minus beta over square root the whole mod square. So that's how we could calculate any arbitrary state in the computational basis in the Hadamard basis. And we could generalize this idea to any arbitrary states and any arbitrary measurement basis. So the technique discussed in previous slides as writing the given state in terms of the measurement basis, and then taking the mod square of the given complex amplitudes, we can calculate the probabilities associated with the outcomes. So is there any uh, more simpler way to write the probability associated with the outcomes in any arbitrary basis? So the answer is yes. So we could calculate the inner product, and making use of the inner product, we could calculate the probabilities associated with the outcomes in any arbitrary basis. So we had state psi, and it is a zero state, and our goal is to find how much plus state and minus state is it in. So we could calculate the overlap of the given state with the plus and minus state, and taking the square modulus square of that overlap, we could get the probabilities associated with that outcome. So we could see that when we take the outcome, the product of or the inner product of plus and zero state, and uh, get the mod square, we get half, and similarly for the minus state. So in that case, we get half probabilities of getting plus state and half probability of getting minus state by measuring the given state zero in other mod basis. So that's much more simpler way to calculate the probability associated with the outcomes, with the measurement outcomes in arbitrary basis, and as in the case of the Hadamard basis. So that's a very good and efficient way to calculate the probabilities outcomes. So moving on to the concept of measuring multiple qubits. So we have a composite state, that is the state the AB, and it is an element of the Hilbert product Hilbert space of the individual Hilbert spaces of system A and B. So our goal is to calculate the is to perform the measurement and then calculating the probabilities associated with the outcomes of that measurement. So first we defined the basis of these measurement. So we could construct the basis by taking the outer product of the basis of system A, and then take and with the basis of the Hilbert space of the system B, and this way we can calculate the overall basis that are required for the measurement of the given multiple qubits and then of the composite system. So taking the inner product of the given uh, basis with the composite state uh, gives us the associated probabilities of that outcomes, and with the and the and the probability associated with that measurement. So it could be explained by a simple example. We have EPR state, that is a very famous state, and it is also called the maximally entangled state. So we want to calculate the probabilities of the outcomes and the measurement associated with the computational basis. So we have both bases in standard basis for the system A and B, and we are calculating the set of bases by taking the product of the basis with of the system A with the basis of the system B. So we get a set of bases, and we have four elements of that set. So we take the Inner product with the given basis and the given state one by one for each element of basis, and we get the resulting outcome probabilities of outcomes. So we could see that the probabilities of getting 0 0 and 1 1 outcome is half. On the other hand, the probabilities of getting 0 1 and 1 0 is 0. This is because the inner product associated with that 0 1 and 1 0 outcomes are 0 because of the nature of the given state. So this is uh, due to the entanglement, and we could see that when a system A performed the measurement on 0 on the given state, uh, he could predict the outcome of the B system when the B system applies the similar measurement on the given state. So that's how the entanglement works. So to conclude today's lecture, we have explored the critical role of measurements in quantum mechanics and its application in QKD. We discussed how to measure single qubits in various bases, including the computational and diagonal bases. We extended this understanding to multiple qubits, examining how measurements are performed on composite or entangled states. These foundational ideas form the backbone of many quantum protocols, enabling secure information exchange and error correction in QKD. Thank you for joining this session. The next lecture, we will explore more fundamental concepts associated with more practical, uh, for the practical use of QKD protocols and its systems. Stay curious and keep unraveling the quantum world. Don't forget to like, comment, and subscribe for more updates.